Our next speaker is Dave Thomas. He is a computer programmer, author and editor, and he has experience in the software industry as an engineer, consultant, architecture and investor. Dave was an original signatory and author of the Manifesto for Agile Software Development, and he is a founding director of the Agile Alliance. Dave Thomas is probably best known as the founder and past CEO of Object Technology International, that is now IBM OIT Labs. He was a principal architect for IBM Visual Age Smalltalk and Java Virtual Machines and Eclipse. Please welcome Dave Thomas.
Well, thank you very much. I'm truly honored and humbled to be here. It would be a privilege just to sit in this audience, let alone to speak. Simula had a huge impact on my life and on the life of many of us building software, most of us, I would say, in one way or another. Unfortunately, I was never able to program in Simula. I'll tell you a bit of that story along the way. When I was called, I was both delighted and terrified. And I thought, okay, I'll get to talk about something, maybe about, what I did with Smalltalk or things like that. And then Berger said, no, we want you to talk about modeling. Modeling. I'm being punished for all those things I said when I was screaming at Ivar Jakobsen and arguing with Trygve and, objecting strenuously to all the horrible things the object management group was doing, or all those case tools, those bad things I said about case tools. What am I going to do? So difficult. So, fortunately, I had the record of Simula and its impact, and it was a chance to think a bit about modeling, about what it really meant. And as Oscar has already highlighted, and I think it'll become a theme through 3 talks from 3 Canadians, I might mention, that there is a harmony that seems to come from programming is understanding the pairing of models and language in a unique and special way. And more importantly, a challenge from Christian and Johan to do better. So let me, first of all, I'm going to go into 40 pages of what is a model. I think Christian settled that early. If he couldn't figure it out in his lifetime, I'm certainly not going to. I think the other thing that's very important is that we need to know that all models lie. Some models lie a lot, some models lie a little, but they're basically just slices of life. They're approximations of reality, they're not reality. And that's one of the things that makes modeling so interesting. This is just a list of some of the things, some of them because people don't even think of QFD, which is a very important model from the House of Quality that often is not considered, although I found it very, very important to allowing users and designers to simply make trade-offs in a little box called the House of Quality. Why do we model? We model to understand, we model to communicate, we model to explore alternatives, we model to refute other people's ideas, we model to simulate, we model to emulate to get more precision, to calibrate, to evaluate, or perhaps to validate, to ensure that we have correctness or that we're meeting some properties that are very important to us. Fundamentally, we model to understand and to manage complexity, because a model not being the real thing is a subset of that reality which we can cope with at a point in time, that we can fit into our brains, and even more challengingly, into the collective group, the collective brains that we have working on a particular problem. In the early years, when people programmed in assembler Fortran, some of you who were lucky in Europe got to use a real language, Algol, or COBOL. Models were largely mathematical. You know, computers then were for solving largely numerical problems, and solutions rendered with numerical methods. Even hearing the appointment of Dahl as a professor of numerical methods some years later still reflected the dominance of that trend for many years. We did have the beginnings of Lisp at that time, so the beginnings of symbolic computing and things like the initial symbolic solvers that led eventually to Mathematica, but by and large, computers were for doing number crunching. And languages had little or no conceptual abstractions. So you had to take the ideas in your mind and formulate them. And often they were specified very precisely for coders with flowcharts. And often the scientist would draw a flowchart for the coder or the programmer, and they would turn that into code in some of the more depressing organizations. Of course, we've heard many times, and may we hear it many more times, the wonderful early years of Simula. What it must have been in the exciting times, and isn't it always true that it's when there's that healthy tension of where people are at their wits' end? We used to, in many of the companies I worked in, have these regular meetings, and all of a sudden, everyone would go around the room and start saying, "We're screwed." And eventually everyone would go around the room. We'd realize that we really had no hope to get done what we were trying to do. At that point, the bottle of scotch would come out, and through some amount of genius, within a few hours, someone would figure out what we weren't going to do, which was the only hard decision to make. Delete that thing, and we would keep moving onwards. But it was that tension of argument, but also that of immense respect. And somehow that point within a group of people that we'd reached the limit of what we could do with each other and perhaps to each other, so that we could then make a decision and move on and get closure. They brought to us the tools of object-oriented programming, and they brought to us a philosophy of computation that will ever be perhaps the most important contribution to problem solving that we've seen. Very, very exciting. They also brought us some little thing called frameworks. Frameworks were really little languages. So they provided an extension mechanism without the syntax of a DSL. That's fairly trivial, but essentially the reason that frameworks are hard to design, and we know that because there's so many bad ones, most frameworks inject dependencies into your program, their dependencies. But these frameworks were designed to enable little languages so you could explore new domains and build little models which you could use. Very, very powerful mechanism. Unfortunately, widely abused by the object-oriented programming community, but it's always difficult when you have a simple idea. I thought teaching Smalltalk to people was a really simple idea, right? It was really simple, and I'm really sorry for what I've done because people made such a god-awful mess that it was really depressing. So really the Simula report had two things about the Simula language. It was provide a language for modeling, for making precise descriptions, and it was provide a language for programming, for computing. And these two ideas are core to what I believe the philosophy is that goes behind what Steve Cook first called the Scandinavian school. And I think for those of us that are here today, and anyone who's been touched by Simula thinks differently, and the whole notion of computation, simulation, modeling, and understanding is at the core of what we believe of how to build software. There are many things that are made in Scandinavia. Modeling and simulation, the approach to complexity. Object orientation. Simula, Delta, a language, an amazing language I've only read up again most recently, thanks to Berger, which was really designed to go deep in the way of describing systems. very, very interesting and something that should be, I think, studied and brought back to life. This would be a great one for, there's a wonderful thing now called, great papers or good papers that are being reviewed around the world, and I certainly think that delta should be on your list. Something that many people don't know about is started in the UK originally, but then spread quickly into Scandinavia, socio-technical systems and participatory design. Perhaps the biggest thing that I gained from my 5 or so meetings with Christian was an appreciation of his passion for having people work together and having a style and quality of work that was important and meaningful. This has been simplified in many cases because when we want to teach something in America, we have to make it into a little book like Scrum or something like that, right? So we don't want it to be too hard. Unfortunately, a lot of things get lost. The essence of things that were behind Agile and Lean and so on, the whole notion of people working together, solving problems, and the notion of actors, both human and machine, collaborating is really, I think, one of the key contributions of the Scandinavian school, and certainly something that Christian championed. Way off in another part of Scandinavia, there was Erlang and the OTP language. Curiously, Joe Armstrong was anxiously waiting his first Tektronix Smalltalk machine, right, so he could begin building his new language and operating system for switches. Unfortunately, Tektronix shipped in the machine with Prolog on it. So he said, oh well, the machine with Smalltalk came and it went to a colleague down the hall, and he says, well, I'll look at that someday. And thereby you ended up with these pattern things in Erlang. But Erlang did solve a real problem, which I think is very important. It really did took the problem of massive concurrency straight on. And it still is the showpiece. If you want to talk about microservices, the first thing you want to do is go to Erlang and look at the OTP patterns because it's a very rich achievement. I was hoping that Trygve might make it today. He's had such a wonderful impact, particularly in the Smalltalk community, with the model view controller, and more recently, his data context interaction paradigm. Very significant contributions. Of course, he also contributed to ORAM, and there was a lot of work on methodologies for use cases coming out of AXE, popularized by Ivar Jakobsen, with OOSE, message sequence charts, role-oriented analysis by Trygve, which really recognized the importance of collaborations. And Trygve's relationship to Rebecca Wurzbach isn't accidental. You can see her work and his work are quite closely related. And of course, OSDL. And of course, it inspired derivative languages, or not derivative languages, languages which borrowed from the great ideas of Simula. And a great deal, some wonderful implementers, all here in Scandinavia. In 1967, Canada celebrated its 100th anniversary. That's Expo 67 in Montreal. Perhaps one or two of you were even there. Very exciting year in Canada. I was a third-year electrical engineering student, a competent Fortran hacker, an ACM reader early on. One of the great things about being around at that time is there were very few books published, so you could actually read almost everything that was in print about computing. We had a real advantage then, right? Yeah. There were very few things, and most of them were really good. Today we have the opposite problem. I was working as a student at the Department of Transport, and basically we were building large simulation models for planning 2 new airports, and where the high-speed turnoffs for the planes were, how they would land, what would happen in snow conditions, and things like that. I was introduced to a exciting language called SimScript2, a discrete event programming language bespoke essentially for the US government. Very excited, had the notion of entities and time advancing and events triggering things. I was just mesmerized. The job I didn't like too much, basically. They had a whole lot of, basically they would interview air traffic controllers to try and capture the logic of how air traffic controllers worked. I guess we could call this an expert system, but of course when you understand how a system works, it's no longer an expert system. Maybe machine learning will be that way too. And so my job was to spend as long as my servitude would allow to convert people's flow decision tables into flow charts and then have those programmed. That seemed like an extremely boring job for me, so I read a couple of ACM articles and found out that there was something called decision tables, and they could make translators and very efficient mechanisms for executing these, so I quickly built an interpreter and a code generator and was able to do a lot more time, as I basically got my summer job done in a month and was able to go off and do some reading and exploring. I also was able to go build a physical model. That's a boat built by a team of engineers where we took a week or two off of class because, after all, we wanted to win the competition in the flotilla parade. And that's my engineering class of the year, proudly going down the river, saying nasty things about the other universities along the way, and perhaps there's an occasional apple or beer. At that point, I became what I would say simulation infected or obsessed. The whole approach to computing by modeling just hit me. It was just amazing. I expected this to take off, and I graduated. I started working in the computer center because in the computer center, that's where things were happening. That's where people worked on programming languages and did exciting things. You could have the whole computer to yourself on Sunday morning. It was just exciting. And some of the programs took the whole morning just to compile. That's when I learned about reading code, because you didn't dare have a syntax error in your program. It could cost you hours. And I wonder, is interaction computing always that good? Maybe it's good that every once in a while you have to get a really slow response, so you have to think about things. Well, I was really excited, but then I found out that, of course, in America, we really know how to do things right. And there's been a solution for solving all these problems. It's called structured analysis design. And this, of course, for Simula became the object winter, right? Basically, we clearly separate the models from the programs, and models are done with diagrams, and code is done with a programming language. And not only that, there are ways to do this which are truly magical, where you have these nice data flow diagrams, which is actually pretty nice, kind of like microservices today. And then there's this funny stuff where you sort of grab the diagram and you shake it, and you end up with something here and something over there, and this becomes the input and the processing and the output, and then the transformation can never be repeated again. I found this truly disgusting, but it did take over for a long, long time. And of course, then there were tons of drawing tools and all sorts of other things. Fortunately, objects came to the rescue. And with a series of conferences that many of us have first met and become very, very lifelong friends, UPSLA, eCoop, OOP in Germany, tools, we were able to share the exciting things we found and learn about different perspectives. In my case, I came to learn about the Scandinavian perspective. In 1989, I was on the program committee for UPSLA, and I was a bit depressed. I can't remember whether it was 88 or 89, because all the papers from Scandinavia were getting kind of pretty bad reviews. And I noticed a similar pattern the year before. Since I'm a very scruffy academic and never really cared about my particular status, I don't know why the university gave me tenure and promoted me. Perhaps I had some Christian properties to me. So I basically said, I don't really understand why you're just knee-jerk rejecting these papers. And they said, well, do you understand them? I said, no, I don't understand all aspects. You know, I can't figure out what this pattern thing is either, you know. But, you know, it seems to me very interesting, and you look at the track record, the papers are clearly well written. The fact that we can't read them is our problem, not their problem. And I said, but since you feel this way, I will be happy to write the authors of all the papers submitted from Scandinavia and tell them they're wasting their time sending them to Uppsala. To which there was some reaction. And the late Danny Bobrow leaned over and he says, well, Dave, what do you propose? I said, I think we should ask, the people from Simula and Beta to come and do an advanced workshop, and the program committee should attend. And to the credit of Danny Bobrow and the other PC members, they agreed. At that point, we managed to crack the code enough that people began to understand and appreciate that there really was a different point of view and the deep value of the Scandinavian point of view. Now, of course, there were lots of efforts to unify model languages and programming languages, but unfortunately, they were largely unknown to much of the world. Delta is a very impressive achievement which deserves much more coverage. In the when, why, and why not of the Beta programming language, Ole and the authors explain the thinking and working in Beta, and some of the achievements they had in terms of being able to deal with the modeling aspects, things like parts in particular. A unique concept in Beta of actually talking about the physical world, the notions of substance, the notion of measurable quality. Think of actually MKS units, for example, and the notions of transformation between states of physical things. Powerful ideas that are still to be explored. I hear Ole's working on a new version of Beta. Wouldn't that be exciting? It really would be exciting. Some of you young people, you have an opportunity. You should take it. And then, of course, in his 2010 keynote, Unified to the Models Conference, a unified approach to modeling and programming, he articulates very well how Simula and then Beta, excuse me, unify the notion of programming and modeling. While this wonderful work was going on, unfortunately, there was an unholy conspiracy. Basically, three amigos, one traitor Swede, two Americans, got together with Rational and probably the biggest Pied Piper in the world, Richard Soley, the chairman of the OMG, still there today, and they created this ungodly monster, UML. Called it a language when it really wasn't. Unified in the name, though a clever orchestration by the OMG, a place where the Pied Piper played to all the methodologists and they all came bringing their little triangles and circles and doodads. And they put them all into a melting pot and mixed it with political ideas and values and created UML, a language with no syntax, a language with no semantic account, and then had the gall to say we're going to do automated code generation from something that doesn't have any semantics, called MDA. And of course, to the critics, they added a secret dose. They went meta. The power of a meta model. Never get into an argument with a person with a meta model, because they can always go further up the reflective tower and redefine the world and then bring it back down. I love 3Lisp. Jim Drivier and I were close friends and worked together, but it was an implementation of a reflective programming language. And I apologize for Eclipse. And I apologize that I didn't even pay attention that when this horrible monster called the Eclipse Moth was being created, which would cause zillions of tools to proliferate all over the world. I'm sorry for your graduate students who you were, and you had to work on these things, building all these difficult tools. Of course, the problem with the MOF is that when you make these extensions, there's no two extensions can necessarily end up in the same heaven. And so the fact that they're compatible is purely an illusion. So the whole notion of protocols is really weak. Now, the other thing, of course, is that, and this is a slide comes from my good friend Jean Bezavin, who many of you know. Jean, of course, one of the people trying to keep models and models transformations on a sound footing, worked very hard for many years. But he showed very simply in this 2003 presentation that basically, the relationships between model elements and the relationships between programming elements are fundamentally different. And we need to be aware of these things. Of course, Scandinavia eventually capitulated. And as Berger describes in this 2011 report, but there's a version online with Hal now, that so you can easily see it. He describes the convergence of ideas in modeling from Simula down into many contributions to UML and UML2. And you'll see the things flowing from Ericsson AXE, where SDL and blocks and so on were found, from those flowing from Simula and Beta and SDL, and then coming in through the ORAM and so on, all contributing to UML. That's what happens, right, when you get a cartel. You have to join them. We should have just burned them. So, key challenges for future languages are making relationships and messages first class. Just think if we could change or reason or have messages as something we could change. We could do a lot of things. We could deal with security outside the object. We could deal with multi-dispatch. We could deal with rule-based dispatch. We could deal with all sorts of things. How about relationships? One of the reasons we have so much problems today with data is we've reduced data to SQL tables, or God forbid worse, no SQL tables. But no SQL will just go away shortly when people realize it's important to actually be able to query the data. But we need to be able to keep relationships first class in our languages, because one of the reasons that object people are so bad with databases is they don't actually understand many-to-many relationships and how important they are. And I can't imagine how many bugs there are because people's models don't do that. And if you actually look at the latest work, for instance, of Facebook, where they've patented graphs for the web, they're very much looking at the entire web as a set of relationships or graphs. We need to be able to support concepts like is like and is approximated by. Very vague and so on, but we can develop some reasoning use some reasoning models, particularly symbolic reasoning for reasoning with uncertainty. We need to be able to represent intent of the machine and interacting with the world, because more and more of our computers have, and our software has interactions with real devices and real human consequences. We need to be able to express architecture and design choices. In our case, we've always put the architecture in the code. Architecture, for me, to answer the question earlier, is really a set of APIs and patterns, the architectural patterns that you need. And they should be versioned in the code as part of the code and clearly visible. If you need to generate a UML diagram, you should be able to pull the code out of Git and run an application that will give you the picture. If you can't, then your architecture, your pictures are not accurately reflecting the code you have. Want to deal with non-functional properties, representing time and space, support for partial specification and relationships between perspectives, and we'd like to have a strong language, as well as tools that let us see it visually. We should not have to have a separate, non-connected visual language or textual language. And it's important in a world where we have so much multimedia that our programs be able to be visually provided. Humans are very, very good at looking at patterns, visual patterns, much stronger than many people think, although we have a lot to learn about how to do visualization and work with visual data, as well as sound. We're very good with sound, but we don't use that. Really good for performance. Some of us knew this in the old days. You could actually tell, you know. Loved to hear that clickety-click of the hard drive and, you know, CPU buzzing. And sometimes the physical is important. And more importantly, we want to be computationally diverse. Objects shouldn't exclude, be exclusive, and deny the ability to express constraints, pure functional programming, nor logic programming. We should be able to embrace those and bring them into a single language. We need to reunite model language and programming languages. This was the great vision of Simula, of Beta and Delta, although Delta was not designed to be a language for computation. We need to stop believing that we can document programs by some well-written code or clean code. Clean code is great for small programs. Systems need more than comments and a few diagrams. Systems need the voice of the designer in them with multimedia, but they also need more expressive paradigms for putting these in our programs. Because given that information, we can check. On almost every project I've worked on, we've built extensive tooling on top of the programming languages and on top of the programming environments to add extra semantics, to check the programs against various constraints, rule checkers as they're called in the chip design business. And for every language and system we build more and more rule checkers, and we're able to get more and more into automation to assist developers with managing the complexity. And that's some of the work that Oscar and his team are working on today, is how to work with programmers. Simula, Delta, and Beta showed the benefit of being able to describe complete systems, both model and code. We need to be able to have systems that we can co-evolve. We can only co-evolve with them if they can play in the same world. We know how to do that with text, so that should be our goal. We may, in the future, know how to do it visually or otherwise. But today, we really still need a single language that can do that. You have the history here in Scandinavia of thinking about things, thinking about models, and thinking about computation differently. You also think about how people figure into the world of computation and how they can work collaboratively together in giving great gifts and lessons to the world on how we can build software in a way that matters and where the software works. I ask those students in the audience to think about this challenge. It seems that the only people who will probably ever take on this problem will have Scandinavian genes. Thank you so much.
Yeah, thank you. We have plenty of time for discussions and questions, so come on.
Or corrective remarks there. One at the back. There's a question at the back.
Thank you for a great talk. Recently, I read a remark by IBM, the CEO of IBM, talking about the post-programming era, where machines are not programmed by humans in the way we are doing today, instructing, but rather that artificial intelligence and other ways of instructing machines like machine learning and everything else in that way becomes the norm, so that the languages will be abstracted away and we won't see code anymore. That's what I hear. Do you have any opinion about that?
I think Oscar has the right answer about predicting the future. I have no doubt that that machine learning will be able to contribute to reducing errors and producing what I'll call configurations of software, for very specific applications. The history has shown that the problems seem to keep getting more complicated and moving on. I think one of the things that does bother me are places that produce jobs for today, where people don't, where they get taught a specific language or a specific framework. I certainly am concerned for those sorts of people and careers, but I think maybe 50 years from now, I don't think that's going to happen all that soon. I also believe that some of the machine learning, the magic will come out of it. And I spent a lot of time doing nonlinear hill climbing and optimization, and neural nets smell an awful lot like that to me. A lot of other people feel that. And if we're going to actually argue correctness for what these programs do, we're going to have to understand a lot more about them. So I think we're at the beginning of a very exciting era, but I believe that the magic has to come out of machine learning for us to feel comfortable with what it's doing.
Thank you for a very good talk, Dave. One of the things I wanted to pick up on was that you've, in my view, I share the view you have of UML being essentially lots of fluff, but with no semantics and so on. On the other hand, it's also been very successful in that lots of people have taken it up and understand and doing it, despite the fact that, well, you can't, as you said, there's no real semantics in the bottom end of it. And so what is it that we actually need to develop to have something like UML at the higher level that actually has a deeper semantic meaning and has something that you can use? Because my experience has been that lots of students have been, they understand some class diagrams and so on, but when it comes to programming, there's like this jump, this non-discrete, it's this break-off jump. And so I'm wondering, what is it that we need to add to have something like UML at the high level that can actually be used at a low level?
Well, I think, just to come back to it, lots of students understand how to do class diagrams because class diagrams are basically trivial, right? And if you put them in a browser, you get indentation, right? And people thought they understood them, but of course, I remember one customer, very large U.S. customer, hired us, and they said, we have a problem with our inheritance. And of course, they had a wonderful small talk program, and it said car, subclass engine, and you know the rest, right? It was a parts hierarchy. So I think one of the problems is that a lot of people think they understand the pictures, but they don't. And I think that's a very good learning experiment to do, is to actually find out what do the students really understand from that versus understand the code, and is it really that different? The other thing I think is that what you want to be able to do is to be able to refine or abstract away the detail from your programs so that you can produce the equivalent views that you get from a modeling tool or a visual tool, because it's nice to be able to see that. But the fundamental problem is, people have to become educated about dependencies. Because the real problem is that the UML story is far too simple in practice, and the reality has to do with the complexities of the design. If we go to value-based, instead of no frameworks with pointers, right? We start going to value-based languages, or at least components, then we can start achieving more of the kinds of goals of doing that. So I think we have to change how we program, at least between components and things like that, and go more to a component assembly model, more towards sort of an Erlang model of messages and values being communicated. And with lots of processes, things get a lot simpler, right? So, you know, microservices are the rage, but it's the hardware that's saving us, not the software, right? It's the fact we can run them cheap. But I think you know, tools can produce those abstractions.
Yes, but what I'm looking for is what is the abstraction I will be teaching the students to make them understand what you just described?
I think they're the same abstractions you find in the programming language, because all the modeling tools essentially try and have something that is isomorphic to a programming construct, or else they don't work, right? So a lot of the executable UML things basically picked one thing. Okay, we'll do state machines, for example, or we'll do activities in a particular net. And so they basically already had a code generator for that, and they just found a UML syntax that allowed them to express that subset of computation. But they're not essentially Turing complete UML.
Okay, thank you.
Thank you.
Well, I think that your talk was really good. I'm myself a student of Ole Dahl, and I'm full of admiration for what he and Dahl and Nygaard achieved. But you know that everything in life, they have a backside. So if we look at the Simula language, so far today we have heard a lot about all the positive things. But could you say something or comment on if there are any negative effects or something that was not that good that was brought in with the Simula language?
So I did say at the beginning that I was not a Simula user. So my knowledge of the language is one of reading code, not one of writing code, and that is a big disclaimer. We did a lot of work in multiprocessing and multitasking in Smalltalk and later in Java, and I think the Smalltalk started with a concurrency model that was based on coroutines. It's a nice model, but if you go to we were working in real time and embedded systems, and we needed to have something that dealt with real threads and real tasks and concurrency and shared memory and things like that. Those were things that weren't in the language at the time. They weren't in the machines that were available at the time either. So that's certainly one area which I found Simula and Smalltalk. So Smalltalk was really very much modeled on Simula to be particularly weak.
Can I pose a question myself then?
Sure.
Because Ole Dahl was my professor, and I think he didn't care much about encapsulation in the meaning that it was okay for all other parts of the program to see all variables and all private, what we now call private methods. You think that's an achievement, that we have now more differentiation between the interface and the internal, or is it could they have some point when they say that it's okay to see most of the implementation as it did in Simula?
So I've always believed that you should always get the source to read and not necessarily have the right to write the source. So because I think it's very important in many cases to have the source for understanding. I think being able to turn the dials on visibility would be very nice. You know, we now have very simple rules, and they get more complicated. It's private, public, private, semi-private, you know, all these things. And I think what we really want to do is maybe have something that's more, actually have a description that can talk about scope. I mean, if you look in the latest Scala, Martin Odersky at PLDI talked about this thing which I would call context, and implicits as it's called, which exist in Haskell, and they list in Scala. And it's a very complicated mechanism when you do all the type theory to actually have essentially what amounts to a non-local reference. There are times when you really do want to have a non-local reference. And I think what we need to be able to do is separately express the constraints on scopes and the rules. And I think if we had a mechanism for doing that in a language, we'd be able to have a very powerful extension where we could control some of those things and visibility. Right now, we want to do it just by declaring it. Same thing with types. I mean, I'm very interested in types, but I really want to be able to talk about what we might call a session type. I want to say that a file satisfies a property, open, read, write, close, open, read, write, star, close. So I can talk about the pattern of messages that goes to the file. But that's a type that I can't define in most languages. I might in a dependently typed language. So I think, you know, given more flexible mechanisms as opposed to just having a name, public, private, and be able to talk about those things, one could reason about those programs and provide more control, especially for very large systems.
Thank you. As organizers, I would like to also pose a question. There are, in my view, on programming, there are two different schools. It's a theoretical schools where you make models or programs, and then the other ones where you make programs that are model of the real world. I mean, do you agree with me that models of the real world is far more complicated and far less, they will not success easily? I mean, it's as you talked about meta models, is that the same? I think it's too much modeling and too little programming these days.
I don't want to be unfair, but I certainly find that going meta often obfuscates the problem, because you have to be able to think at these multiple levels. And, you know, the real meta-programming stuff is called procedural reflection, which is a challenge by Brian Smith. And no one, to my knowledge, has actually published a paper on a procedurally reflective language. You know, so I think you start getting pretty philosophical quickly, and I think it's easy to get lost in levels of abstraction. And it's very hard to have an argument unless you're kind of not in the same world, right? So you're talking to this other person. So I think it's much easier just to build more and more models of code. So you build what you can understand, and you execute it. In fact, our whole methodology is we build everything 3 times, usually 4 or 5, but we like to say 3. You know, once conceptually, very quickly, just to sort of see whether anything hangs together. A second time to actually make it work, and then a third time to make it, you know, fast enough and small enough that you could actually ship it to somebody and they could use it. And sometimes it takes 4 or 5. So I think it's the success of refinement and the ability to model what you can and leave out the other part. So getting something done, because part of being successful is, you know, shut up and ship, basically. So if you can ship code and the customer's happy, then you get closure, and somehow you get that energy to go back and tackle that part of the system you don't understand and work on it. Sometimes you actually do things that you don't understand and you know it. And I think that's the ones we have to try and find a way to hold back on. Intrinsically, we know we don't have the right solution. This is fine if it's a website. It's not fine if it's something that's driving a car or controlling other things. And I think we really have an education job and a language design job and a lot of issues for how we can deal with safety and the care with regard to these systems. I'm particularly concerned about the use of techniques we don't really understand. I think machine learning is amazing, but we really need to understand more of it before we decide to turn over a big part of our society to these sort of robots trained by lots and lots of data.
Okay, other questions, comments?
One at the top. No, take the phone up.
The back first.
Eric's already had one. He's going to ask the harder one.
Yeah, thank you for the talk again. So I actually want to pinpoint on one of the points in your talk because I probably didn't understand that correctly, or maybe we are doing something wrong. So
or maybe
actually,
I'm wrong.
Yeah. So you said that we need to be able to co-evolve models and the code by expressing both in a single language. Yeah. The way we do it, for example, yeah, we take one language to build the models, and then we take another language to define the semantics and build our generators, which in turn actually generate code in the third language, which is in turn compiled and executed, right? So this is how we do it right now. So what do you mean by, how do you see it, this workflow having a single language?
So I would say you're in essentially the DSL transformational school, right? That's sort of the Scala model today, typically. But I don't think there's anything wrong with that. The problem is there's a lot of semantics going on and a lot you have to know, right? Whereas we basically start and model things that we're interested in much more concretely, just using classes and methods, which was essentially the approach in Simula, as opposed to trying to have all these generators and so on, which is from my point of view, quote, hidden magic. We actually just model things directly in a framework. If we want to put a syntax on top of the framework, because language design is already very hard. And the nice thing about doing language design with a framework is you focus on just the language elements, you don't worry about the syntax. And so your semantics is very concrete because you're using a language you already know to express it via classes and methods. And then if you do decide that you need a syntactic sugar on top, that's fairly straightforward because it's just a parser that, essentially, assembles these things or creates a linguistic transformation. Otherwise, you have to build this whole set of pipelines and tools, which works for really clever people who usually go and work someplace else after I've hired them. DSL is a really powerful tool, but it's only justified if it's going to make massive productivity in your organization. And if you use a DSL, you need 2 people to maintain it. Otherwise, you're on a DSL island, and when they leave, there's nothing wrong with using a DSL. It's a very good tool. If it's going to enable 20 or 30 or 300 people to be more productive by using this DSL, then it's a great thing. But you need to maintain and document and understand that DSL. Versus directly expressing it in a framework is much simpler, not nearly as sexy. But that's why I would say the approach would be to model it directly in the code.
But then why do you think that we need yet another language? We have a language, so you can take any language, Python, Java, or whatever, and
you can, but you can't make. Well, for example, one of the real problems with data and data abstraction and all sorts of problems is the fact you can't talk about relationships in a language. There's no semantic, no way you can express a many-to-many relationship in Java in the language. That's an extension that I would want. So because there's a whole part of the world that has to deal with the complex relationships with data. It makes querying easy. You find all sorts of bugs, navigation and so on. Working even at a relational level is a lower level machinery. The real abstraction is a set of relationships which get compiled down into tables. So I want to be able to keep that model and execute against that model in my programming language in a first-class way so I can navigate those relationships explicitly by name. Just one example.
Yeah, thanks.
Okay, it seems like I actually get a chance to give a second question. And that's looking a little bit forward from Simula. You also mentioned beta. And so my question is, I think beta is an impressive thing, but what is the basic, what's the basic thing that you think is the best improvement upon Simula that beta contributed?
Well, I'm not a beta expert, again, so let me make that clear. Ole can jump in. To me, the thing that's very important is that for years we've been worried about talking about part ofs, right? And the ability to deal with, composites and so on. And beta supports a very nice handling of composites, the ability to address both the whole object and the elements inside the object. The other thing that I think is very exciting, but which isn't really, from my point of view, and maybe just my reading, well explored, is the whole notion of being able to model the physical world. I mean, it's well known that, for instance, lots of errors happen because of people having unit errors. I mean, it seems today if we're writing programs that deal with the real world, we should be able to talk about centimeters and inches and things like that and have, you know, checkers that can check those checkable properties. There have been systems done over the years that do this. I don't know what's going off here. It's just telling me I'm over. But I think that work with the transformers and so on is also very interesting, so I would certainly like to see those extended. So those are two things.
So the buzzer says it's over, so then it's probably over. Thank you very much.
Thank you.